Chris from the future here. I have to start this video by showing you the mother of all ESC voltage spikes. Huge thank you to Luke Maximo Bell for allowing me to share this clip. Hi there everyone and welcome back to the channel. If you've ever had an ESC spontaneously catch fire, particularly when you're disarming your drone, or you've had an ESC catch fire during a crash, you may have been the victim of a voltage spike. In this video, I'm going to be doing a deep dive set of testing to look at how these voltage spikes come about, what causes them, and how we can mitigate them with capacitors and TVS diodes to try and minimize the chance of any of our ESCs bursting into flames. This video is a response to a couple of questions that I received and also an issue that Luke Bell has been facing with his world record drone, where he has often seen ESCs spontaneously catch fire, particularly when disarming the drone. This is going to be a really interesting video. I've done heaps of testing. I've got lots and lots of data to share with you. So let's not waste any more time. Let's dive right into it. So let me take you through the equipment that we're going to be using to make these measurements. Starting with the motor. This is a 2207 1850 kV 6S FPV motor with a 5 by 4.3 by 3 prop. So kind of standard 5-inch FPV setup. And we also have an RPM sensor here so that we can spin this motor up to exactly the same RPM for each test. The motor is connected to a SkyStar's KM55 amp AM32 ESC, and on the battery leads of this ESC I've connected two stiff copper wires, one to the ground and one to the positive battery voltage. The ground lead has the two ground connections for the oscilloscope probes connected to it, and I have one oscilloscope probe connected to the positive battery lead and one to one of the wires to the motor, so we can measure the voltage on one of the motor phases. The two oscilloscope probes are connected to this Handtech USB oscilloscope so that we can log the data and gather all of the information and record it onto the computer. And then in terms of power, we have two batteries. We've got a 4S 5000 milliamp hour and a 6S 5000 milliamp hour, and they're both kept topped up to the right voltage by this power supply here. In general, this is pretty representative of what you get with a single motor and single ESC, and we are going to be able to measure the size of the voltage spikes that we get from both the motor just running and also actively braking, with no capacitor attached, and then with capacitors and TVS diodes attached to the ESC as well. And here we have the components that we're going to be testing on this rig. We have a 1000 microfarad capacitor and a 470 microfarad capacitor. We have a capacitor with short legs and a capacitor with the legs left long. And we also have this FETTech spike absorber, which is a set of TVS diodes, transient voltage suppression diodes, which are also commonly used to try and mitigate voltage spikes in electronic circuits. So we'll see how well this works at mitigating the spikes on our ESC. All right, so now I'm going to take you through some live data collection so you can see exactly how I collected the data that we're going to be looking at in the rest of this video. I have my USB oscilloscope set up on the screen. I have the test stand set up back here. I'm only going to be running this at a very low RPM because obviously I'm here recording. Normally I would go and stand away from the whole test setup while it's running. But we're going to collect a little bit of data now so you can see what we're going to be looking at. So first things first, safety specs on. And then I'm going to power this up just with a 4S battery. I don't want to run it up to high voltages. And you can see that immediately we start hearing the ESC beeping. And if I go to the oscilloscope screen and I bring this trigger level down, you will actually be able to see that the oscilloscope is measuring the beeps. And we can actually look and find the height of the spike when the ESC is just beeping. So just when the ESC is beeping, we haven't got any capacitor or anything on this, we're getting up to a spike of about 18.5 volts on a 16 volt pack just from the ESC beeping. Now what I'm going to do is I'm going to start the motor spinning just nice and slowly, and then we can see what the trace looks like while the motor is running. So I'm going to run the ESC up to just a pretty low speed. Let's go for 5,000 RPM initially. So again, now I can bring down the trigger level and we can see what the ESC looks like while it's running. And again, we're getting kind of an oscillating voltage on the battery lead, exactly as we would expect. And that oscillating voltage is looking to be around 18 volts. Now, if I increase the RPM of the motor a little bit, you'll see that the spikes get a little bit bigger. But we can kind of get the idea. The faster the motor is running, the higher the spike is going to be. Again, this is without any capacitor or TVS diode in place. Now what we're going to do is we're going to try and collect some data when the motor is actively braking. And the way I'm going to do that is I'm going to turn the trigger voltage up a little bit. I'm going to set the trigger mode to single shot. And now you can see that we're kind of seeing what's going on with the trace, albeit a little bit slower. Now I'm going to disarm the ESC and actively brake the motor. And there you go. The motor has stopped spinning and the trace has stopped because we've hit our trigger point. I'm just going to unplug the ESC so it stops beeping. But what you can see is that we have actually a much bigger spike when the motor is actively braking than when it's running. And that's what we're going to see throughout the rest of this video. The spike from this motor braking is just around, maybe it peaks at 21 volts. And remember, that's 21 volts on a 16 volt battery voltage. So we're getting quite a big spike over and above the maximum battery voltage that this ESC would ever see if you plugged in even a fully charged pack. It's interesting to note that as well as obviously the big spike on the battery leads, we also see a big spike on the individual motor phase wires when we're doing this active braking. So this motor phase is momentarily hitting a voltage of about 25 volts. Which is 9 volts more than the 16 volts that we're actually supplying from the battery at this moment. So it's worth being aware that you're going to get voltage spikes not only on the battery leads but also on the individual motor phases during active motor braking like this. So now that you've seen how I collected all of this test data, let's dive into the results and take a look at how these voltage spikes change depending on RPM, battery voltage, and how effective capacitors and TVS diodes are at mitigating their effects. So let's start by looking at the data collected at 4S battery voltage with no capacitor and no TVS diode fitted. So remember, there are still capacitors on the ESC, but we're just not fitting any extra ones. Running at 10,000 RPM, we get spikes up to about 20 volts on the battery lead, and the voltage drops as low as about 13 volts at the bottom of a dip. So we're getting about a 7 volt peak to peak on the battery leads. The motors are spiking even higher. They're spiking up to about 22.5 volts. And again, this is while running at a 16.1 volt average battery voltage. If we then start to brake the motor, so we disarm the ESC for active braking, we get a spike up to 25 volts on the battery lead. And we actually don't see the biggest spike on the motor phase here because that's a different phase of the motor that we're not connected to. We do see a spike to 25 volts on the motor phase that we are measuring. And that's just at 10,000 RPM, which is like probably not even hover throttle. It's like even below hover throttle. If we go up to 15,000 RPM, now we're getting spikes up to 21 volts on the battery lead. So those spikes have got even higher. We're looking at an 8.5 volt peak to peak. And then we see spikes up to 26 volts on our motor phase while the motor is running. Just at this moment here, which I guess perhaps is a measurement period on the drive of the motor, I'm not sure. But again, we're still only at 16.1 volts average battery voltage. So we've got spikes up to, up into the 6S voltage range now. If we look at active braking at 15,000 RPM, so disarming the ESC at 15,000 RPM, which is like a hover throttle for a pretty heavily laden quad, would be up at sort of 15,000 RPM. So you might disarm from that level. You're getting spikes up to 27.5 volts on the battery lead, spikes up to 21 volts on the motor phase that we're measuring. But, we can expect higher spikes on the motor phases that are being actively braked first. And again, this is just on a 16.2 volt 4S battery voltage. At 20,000 RPM, spikes to 19 volts, spikes to 25 volts on the motor phases. Bit of a lower average battery voltage because obviously now we're drawing a lot more current. And that is kind of the competing factor. As you draw more current, the average voltage drops, but the size of the spikes can still be pretty high. What's really interesting is when you start breaking from really high RPMs. Here we're getting spikes to 28 volts on the battery lead, and we happen to catch the right motor phase to get the first breaking spike. And that spikes up to 33 volts. So it's more than twice our average battery voltage is momentarily being applied onto the FETs on the ESC, just at the moment where it starts to break the motor. And you can see that this spike doesn't last all that long, maybe 10 microseconds or so. But it does kind of ring away as the motor slows down, as the braking takes over and the motor comes to a stop. I went up to 25,000 RPM, same spikes to 19 volts, spikes to 23 volts on the motor leads. Now we're down at a 15.4 volt average battery voltage because we're drawing a lot of current, so there's voltage sag from the battery. But we're still getting spikes up to the same sort of level that we were getting at the lower RPMs, just because our peak to peak is a little bit bigger. When we look at the braking for 25,000 RPM, that's where we hit the biggest spikes that I measured on 4S voltage. So spikes to 30 volts on the battery leads, spikes to 35 volts on the motor leg. And again, we just happen to be fortunate that we catch the start of the motor braking in this test. So the phase that we're measuring is the first phase to start measuring, to start braking the motor, and therefore gives us the highest spike. And we've got an average battery voltage of 15.8 volts. So we're spiking to way above twice battery voltage on the motor phase. If you're interested to look at all of the raw data from this testing, I'm going to post it all in a PDF on my Patreon, so you can sign up for just a few dollars a month, and as well as supporting this channel and helping me make more videos like this for everyone in the community, you'll also be able to download all of that data to look through it at your leisure. If that interests you, then please check out the link down in the video description. So far, so terrifying, right? I mean, these voltage spikes were a lot bigger than I was expecting, and we're still only using 4S battery voltage. Let's take a look at some of the more extreme results for 6S now. So now let's take a look at the most extreme results on 6S battery voltage, no capacitor, no TVS diode, and the highest RPMs. Looking at the 30,000 RPM, which is pretty much wide open throttle at this point, we're getting spikes up to 32 volts and spikes up to 34 volts on the motor phase while the motor is actively running, and that's with a 23.1 volts of average battery voltage. If we then brake the motor, we see spikes up to 44.5 volts on the battery leads, spikes to 28 volts on the motor. And it's interesting to note here that with the 6S testing, the voltage starts to dip at the start of the motor braking, whereas on 4S, the voltage always rised at the start of the motor braking. I'm not sure exactly why this is. Perhaps someone who's familiar with motor commutation would be able to explain it. But it seems like the peak occurs just after the start of the braking rather than like immediately when the motor starts to brake. Average battery voltage, 23.8 volts during this test. So we're getting spikes up to not quite double the battery voltage, but pretty close on the battery leads. And I can imagine that the motor phases could even potentially spike higher than the battery leads, although obviously it's very hard to catch that actually happening. We're going to start by looking at the 470 microfarad low ESR capacitor that's supplied with most 20x20 and 30x30 ESCs. And I've mounted it by cutting the legs as short as possible and soldering it directly onto the battery pads of the KM55 amp ESC. So this is kind of the ideal mounting situation for a capacitor where it should be able to do the most good. So I'm going to skip over the low RPM tests because they're not super interesting and jump straight to 20,000 RPM. Now we've done exactly the same test, but with the 470 microfarad capacitor with short legs soldered across the battery leads. And it makes a huge difference to the size of the voltage spikes. We see when the motor is just running at 20,000 RPM, we barely get any spikes. We've got a 15.8 volt average and a spike on the battery leads up to 16.5 volts. That is totally different to what we saw without any capacitor. It really reduces the level of that spike, and honestly there's very little fluctuation in battery voltage. Interestingly, we do still see spikes on the motor leads, and although those spikes are now to a much lower level, those spikes, up to about 19.5 volts in this case, are still significantly above the voltage that we see on the battery leads. So we still do have to be somewhat concerned about the voltage that individual motor phases might be reaching when the motor is running, even if we put a capacitor across the battery leads. Obviously 58 volt average for this test. If we now move on to the braking, we see again a vast improvement. I mean, we're talking about now having spikes of just a couple of volts up to about 18 volts. And the motors are spiking up to 22.5 volts. So the motors are still spiking up to a higher voltage than battery voltage by quite a significant way. But the amount of spike is just completely different to what we saw without any capacitor in place. So the capacitor is reducing the size of the spikes both on the battery terminals and also on the motor phases. If we look at 25,000 RPM, again, we don't really see much in the way of spikes when the motor is running on the battery leads. On the individual motor phases, we're getting spikes up to 21 volts, which, although it's a lot higher than 16 volts, it's still nowhere near what we were seeing without a capacitor. And we got a 15.3 volt average just because the motor's under more load, drawing more current. On the 25,000 RPM braking, we kind of get a perfect worst case test where we catch the first motor phase that is braking the motor. We get a spike here up to 24 volts on the motor phase, but the battery voltage only spikes to about 17.5 volts. So you can see that at this point, if we've got that capacitor with the short legs soldered across the battery leads, we probably don't need to worry about spikes in battery voltage anymore. That seems to be well handled, but we might still want to worry about spikes on the individual motor phases, particularly if we're running at much higher voltages. One of the things that pilots are often concerned about, and I think justifiably so, is the length of the legs on the capacitor that they solder to the ESC. Obviously, there's a concern that if you make the legs too long, the resistance of the wire between the ESC and the capacitor reduces its effectiveness. To test this, I did a test with the capacitor leaving the legs as long as possible to see how much that affected the efficacy of the capacitor at smoothing out those voltage spikes. So here we're looking at exactly the same test setup and same test method, and actually the same 470 microfarad capacitor, but this time the legs are 20 millimeters long rather than as short as possible. So they're left as long as they can be. What we see is that we do get a bit of a degradation in performance with the longer capacitor legs, but the degradation is not massive. We're looking at between 0.5 and 1 volt of increase in the size of the spike on the battery leads by leaving the legs to 20 millimeters long. So we're getting a spike to about 17 volts at 20,000 RPM, a spike to 22 volts on the motor phase, and that's with a 15.9 volt average voltage. If we then look at the braking, again, we see a bit of a bigger spike, so 18.5 volts rather than 18, but it's not a big increase in the size of the spike at all, and a similar size of spike on the motor leads. And the same is true at 25,000 RPM, 17 volts, 21.5 volts on a 15.4 average. And the braking test, we get a spike up to 18 volts with a motor phase spike up to 23 volts. Again, this is the worst case because we caught the first phase, and that's on a 16 volt average battery voltage. So yeah, based on this testing, I don't think we need to be overly concerned about leaving the legs of the capacitor just a little bit longer. It doesn't seem to degrade performance all that much, but I would suggest that it is overall better practice to try and keep the legs of that capacitor nice and short. And if you do need to make the legs longer, consider using some leftover motor wire or something like that, so that when you extend the capacitor legs, you're using thicker wire with a lower resistance. But overall, based on this, we shouldn't expect to see a huge degradation in performance just from having slightly longer legs on our capacitors. Here's the data from the 1000 microfarad capacitor, and overall I really didn't see any improvement in performance moving from a 470 microfarad up to a 1000 microfarad capacitor in this testing. We might be well into the region of diminishing returns, but we can see that we get a spike to 24.5 on battery voltage while the motor is running at 25,000 RPM, a spike on the motor phase to 32 volts, and that's with a 23.6 volt average. Under braking, we spike up to 26 volts with an individual motor phase spiking up to 33 volts, and that's on a 24 volt average. Honestly, I couldn't see much difference in performance between the 470 and the 1000 microfarads. Perhaps if you had many more motors, you had 4 motors on the ESC rather than just one, and you were braking all of them at the same time, you might see a benefit from the 1000, but I couldn't see anything for the 470. So capacitors work really well on the battery leads, but there is another way to mitigate voltage spikes, which we haven't talked about yet. So for those of you not familiar with TVS diodes, this is a quick explainer. This is a FETtech spike absorber, and you can see it's got 3 components on it, and they are 3 TVS diodes, or transient voltage suppression diodes. They're Zener diodes, which this is the electrical circuit symbol for them. And what they do is they help manage spikes in voltage. So without any TVS diode present, let's say we have a spike in voltage coming along, so we've got our battery voltage, and then suddenly we brake our motor and we get a big spike like that. And we're worried that the top of this spike is going to be such a high voltage that it might damage components. And, you know, that could be really bad for our ESC. So we have this thing called a TVS diode, and with a TVS diode, you use it a little bit differently to a regular diode. Normally, you would apply positive voltage on this side of the diode, and it would flow through the diode. That's how like LEDs and stuff work. But with a TVS diode or a Zener diode, you actually apply voltage the other way. So you apply positive voltage here, and the diode doesn't conduct electricity. So it just sort of is an insulator. As this voltage builds up and up and up, eventually it reaches a point that's called the breakdown voltage of this diode. At this point, the diode can no longer resist the reverse bias, the reverse voltage, and it breaks down. And it does that really, really fast. It breaks down in nanoseconds or even picoseconds. And a huge amount of electrical current is suddenly able to flow from the positive to the negative side, because we've got this big reverse voltage, and suddenly this diode breaks down and conducts really, really well. As soon as this voltage falls back below the breakdown voltage, the diode stops conducting again. And this has the effect of basically chopping the top off this spike. So the voltage is coming along, it spikes up, it hits the breakdown voltage of the diode conducts really well, a lot of current flows through the diode, and the voltage is unable to climb any higher and stays at that level until the spike is finished, and then obviously comes back down again. And this level here is called the breakdown voltage level of the diode. So this approach we can use to mitigate the spikes on the battery leads of our ESC by soldering the Zener diode across the battery leads in such a way that the positive voltage is applying reverse bias to the diode. So now we've talked through how these TVS diodes work, let's see how they perform in practice. So all of these tests are conducted at 6S voltage. We're going to start with the 10,000 RPM. You can see that we are getting spikes to 27 volts when we have just the TVS diode in place with no capacitor. So you can see that that's pretty similar to what we were getting when running 6S voltage with no capacitor and no diodes. We also see spikes to 29 volts on the motor phases. When we move to braking, we see a spike up to 30.5 volts, but you can see that the spike is no longer a sort of nice decaying sinusoidal spike. We now have this sort of weird little shape here, this little step. Now, obviously it's not a perfect chop of the top of the peak like I showed in my drawing, but as you'll see, this already has the TVS diode starting to work. You can see that it helps cut the spike, but it's still reaching about 30.5 volts. So it's a lot higher than what we have with the capacitor. And we see an even bigger spike on the motor phase, because obviously the motor phase can spike up even a little bit higher than what we see on the battery leads. If we go to 15,000 RPM, again, we see that we're now getting still spikes up to 30 volts and up to 29.5 volts on the motor phase. And during braking at 15,000 RPM, we can see the spikes a little bit higher, but now that change in shape is starting to become even more obvious. We've got a kind of little spike, and then suddenly the spike kind of stops and comes back down and then stays at this level. That is the TVS diode kind of cutting in, breaking down and starting to conduct, and it basically chops the top off that spike. So that keeps it to about 32 volts at a maximum, with obviously a kind of breakdown voltage here of somewhere around 30 volts. It doesn't stop the motor phases spiking up pretty high though. We're still seeing spikes up to 38.5 volts on the motor phase, but the shape again is different because you can see the conduction of the TVS diode here is kind of chopping the top off what would otherwise be a nice rounded kind of top of a sinusoid. At 20,000 RPM, we got spikes up to 30 volts, spikes to 29.5 volts on the motor phases. But then under braking, even though we're at a higher RPM, we don't see a higher spike. Spike still gets up to about 31 volts. You can see it being cut off both in the battery leads and in the motor phases as well. This keeps going. We go to 25,000 RPM and you can see that we're getting now spikes up to 30 volts just when the motor is running. Spikes to 36 volts on the motor phases, but under braking, again, only up to about 32 volts. So we keep increasing the RPM, we keep increasing the expected size of the spike, but that spike doesn't actually materialize because the TVS diode kind of clamps the top of it and that voltage just dies away. However, we are not getting anywhere near the performance that we saw with the capacitor because we're still getting spikes up to 32 volts, whereas before we were seeing only spikes of up to sort of 26 volts. And we're seeing commensurately much higher spikes on the motor phase as well, even though the TVS diode is doing its job and conducting to kind of chop the top off the peak. So what conclusions can we draw from all of this testing and all of this data? Well, I think the first is that definitely don't find yourself in the position where you are running an ESC without the supplied capacitor soldered onto it. The spikes that we were seeing are at least double battery voltage if you don't have a TVS or you don't have a capacitor soldered onto your ESC. And there's only so much abuse the FETs on an ESC are going to take before all of that over voltage just starts to degrade them, and eventually they will fail. When they fail, they usually fail short circuit, and that's going to burn the ESC and cause the quad to fall out of the sky. So definitely don't run an ESC without a capacitor soldered to it. Try and keep the legs of the capacitor short, but it's not the end of the world if they happen to be just a little bit longer. The main thing is they fit nicely in your build and you have that capacitor soldered on. A capacitor on the battery leads is going to be doing a much better job than just a TVS diode. A lot of modern ESCs actually, like this T-Motor F55 Pro 3, actually come with a TVS diode on the board. I don't think that's going to do anything if you also have a capacitor soldered to the board. What it will do is provide some protection for the ESC in the event that someone runs it without a cap, because then the TVS diode can step in and kind of chop the tops off those peaks and help avoid overvolting the whole ESC. But if you've got a capacitor soldered onto the ESC and that capacitor is working correctly, then the TVS diode probably isn't doing anything. It's good to have it there though, because if the capacitor fails or comes off the board, then the TVS diode is your fallback and it's going to protect the ESC, help you get to the end of the flight, and then you'll spot that something's wrong with the cap, repair it or replace it, and you won't burn the ESC. In the event that you're trying to do something really, really extreme with your ESC, for example, you're going for a world drone speed record, then certainly you're going to want a lot of capacitance on the ESC. Certainly you're going to want a TVS diode on the ESC in the event that the spikes are even more than the capacitors can deal with. But I think there's another thing to think about, which is the voltage spikes on the individual motor phases. that can also be a problem, because if those get super big, they can get a lot bigger than the spikes than you see on the battery leads. So the battery lead spikes will be at some level. The motor phases could spike to an even higher level than that. It's not appropriate to try and solder capacitors across the motor phases, because if you put capacitance on there, it's going to mess up the ESC driving the motor, cause all sorts of problems. But you could consider using TVS diodes across the motor phases with a suitable breakdown voltage that's just a bit less than the breakdown voltage of the FETs on the ESC, so that in the event that you get a big voltage spike on the motor phases, the TVS diode can step in, conduct away a bit of that spike and just protect the FETs on the ESC. That might help prevent some of the pretty extreme ESC fires I've seen where drones have been disarmed and just burst into flames. In any case, I really hope you've enjoyed this deep dive and that you've got some useful learnings from it. Certainly, I really enjoyed making the video. I hope you enjoyed watching it. That's all I have for you until next time. So until then, I wish you all very, very happy flying.